All right, so to start us off on this continuation of separation of variables, I'm going to show you some pro techniques, things that often come up whenever we have taken our antiderivatives from our differential equations. We have some absolute values in there. We have some other constants we got to deal with. How are we supposed to deal with it? So the first one is the absolute value situation. So let's say that we have the equation over here on number 1. The absolute value of y is equal to x, and so we want to solve that thing for y. So you do it the same way that you solve y equals the absolute value of x. We've got to get rid of the absolute value symbols, and that's going to leave us with a plus or a minus. Okay, plus or minus, that's over there on the left-hand side, but we could just multiply by minus plus and then get it over to the right-hand side. Okay, so let me come back up here to the absolute value of y is equal to x and rewrite it as a piecewise equation here. So whenever I rewrite it as a piecewise equation or piecewise function, it's actually not a function because I'll show you the graph of this in just a moment. X should be equal to y as long as y is greater than or equal to 0, right? So absolute value means, and then, but if y was negative, then I have to negate y because that's what the absolute value will be. So x would be equal to negative y whenever y was less than 0. Just a moment. I'm going to come back to this, and I'm going to take a look at the graph in a little bit more detail. So the second one, we're going to use some properties of exponents to simplify y equals e to the x plus c. Okay, so rewriting the equation. Whoop, screen time. It was up 17%. Is that what that said? Okay, so we've got y is equal to e to the x times e to the c. What I just did there is I used the multiplication property of exponents, that whenever I'm multiplying with like bases, which is basically what I'm doing in this stage right here, this simplifies to keeping the same base and then adding the exponents. I'm just basically working that process backwards. And the reason why I did that is because e to the c is some sort of constant value, which I'll call k. Now, in this particular case, you want to make sure that you're kind of careful about this, because e to the c cannot be absolutely anything. Whenever I raise e to some power, if I take a look at the graph that's over here, whenever I raise e to some power, it's always a positive number and never 0. And so I might have to put some sort of constraints on that particular constant, okay, so that k is greater than 0. So I'm going to come back over to example 1, and I'm going to explain that one in just a little bit more detail here. Maybe using an orange crayon. Okay, so when I just defined right over here this absolute value of y is equal to x as a piecewise equation, let's take a look at what that graph would look like. Okay, my coordinate grid. Now the first part, x is equal to y whenever y is greater than or equal to 0. So y greater than or equal to 0, of course, means the top part of this graph, right? Okay, so x is supposed to be equal to y. That's the same thing as y is equal to x, and it's going to be this portion of the graph. Okay, the bottom part says that x is equal to negative y whenever y is less than 0. So it's supposed to be x is equal to negative y. And of course, we usually don't think of stuff like that. Instead, let's move the negative over to the left-hand side, and that's negative x is equal to y, or if you prefer, y is equal to negative x. Okay? All right, so y equals negative x is this graph right here. But I don't get to keep all of it. I only get to keep one part of it. So this is saying that whenever y is negative, when y is less than 0, I use y is equal to negative x. So this portion of the graph is not when y is negative. It's when y is positive, which means that I have to use this bottom part of the graph that's over here. Okay, and I'm going to get rid of this part. And not the axis too. Geez. All right. Be careful. All right, there you go. Another way to think of this is like this. The absolute value of y is equal to x is just the inverse of y is equal to the absolute value of x. The reason why is because we've just switched the x variable with the y variable, and whenever we graph inverse functions, we're supposed to reflect that thing across the line y equals x. So here, let me kind of draw some of this stuff in here. So let's say that I have y equals x right there, and the original absolute value function would have looked like this, and then when I reflect that green graph across the purple line, I get the orange graph. Of course, colors make sense. All right, let's look at one more pro technique, again involving some absolute value. I have no idea why that's right in there. Didn't animate that correctly, I guess. So solve the natural log of y is equal to the natural log x plus c for y. Okay, so rewriting the equation. And then what I want to do is I want to exponentiate both sides so I can get rid of that natural log. So whenever I exponentiate the left-hand side, e to the natural log of y, absolute value y, is equal to e to the natural log of x plus c. And then here's the part that didn't get animated. So we're going to take this e to the natural log of x plus c and rewrite it using that property of exponents that we talked about in the last slide there, where when we're multiplying with like bases, we add the exponents. We're working that process backwards, okay? On the left-hand side, of course, and on the right-hand side, e and the natural log are inverses, so they're going to cancel each other out. And then I'm just going to bring that e to the c right up to the front of this thing, okay? And now what I want to do is get rid of one of the absolute values. We usually want to solve this for y, and that's exactly what this question is asking me to do. So whenever I get rid of the absolute value, then I'm going to replace that with a plus or a minus. So y is equal to plus or minus e to the c times the absolute value of x. And then usually I think of this e to the c as just some sort of constant. So I can take that out and then I can replace it with, I don't know, another constant, which I will call k. All right, I have to make note that k cannot be equal to 0, because if k was equal to 0, I would have y is equal to 0 times the absolute value of x, which means that y is equal to 0. But back here in the original equation, there's no way that y could be equal to 0 because you can't take the natural log of 0. So, and what the heck does this graph look like? It looks like a big old X. Very nice. Okay, so pro techniques aside, let's see if we can put those into action on this next example. Find the general solution of, I've got x squared plus 4 dy dx is equal to xy. Hey, let me ask you a question here. What's step number 1? Did you just say separate the variables? Well, you're totally right. That's exactly what we're going to do. So we've got, let me write it down again. What example is this? It's example 3. And then we have the differential equation x squared plus 4 dy dx is equal to xy. We want to separate our variables, get all of the x's over on the right-hand side, all of the y's over there on the right-hand side. So I'm going to have, let's see, the y needs to come over here. I'm going to have dy over y is equal to, the dx is going to come join the x, and then the x squared plus 4, I have to divide it over to the other side, so it's going to be on the bottom, x squared plus 4. All right, there's that step done. Now I want to take the antiderivatives of both of these sides. On the left-hand side, dy over y, it's the same thing as du over u. That is the natural log of, don't forget it, the absolute value of y. Okay, and then over on the right-hand side, it looks like I need to do a little bit of u substitution here. So switch colors, and I do have down here in the bottom, it's a more complicated part, it makes sense for it to be the u, that I've got x squared plus 4, and my du should be equal to a 2x dx. I don't have a 2, so I need to fix that. I'll put a 2 in there, and then compensate with the 1/2 out front. Okay, so maybe I rewrite this problem thusly, that I have natural log of the absolute value of y. I've already dealt with the left-hand side. 1/2 of the antiderivative of 2x dx is all du, and then the x squared plus 4 that's on the bottom is u. Hey, it's very similar to what we just did on the other side of the equation. This will be equal to 1/2 the natural log of the absolute value of u. And please do not forget your plus c. Okay. All right, and then I need to go back and replace my u with x squared plus 4. So I have the natural log of the absolute value of y is equal to 1/2 of the natural log of the absolute value of x squared plus 4 squared. All right, so, plus c. At this point, you can notice that on at least the right-hand side, the absolute value here is unnecessary, and the reason why is because x squared plus 4 is always positive. But not only that, I'm going to take this 1/2 as this power that's in front, and I'm going to bring it into using a property, the power property of exponents. I'm going to bring it on the inside, and when I do, that's going to make that the square root. So I have natural log absolute value of y is equal to the natural log of the square root of x squared plus 4. Again, the absolute value is not necessary, and then plus c. All right, again, we want to solve this thing for y. We want to isolate the y. So in order to do that, I have to exponentiate so I can get rid of these natural logs. So exponentiate, let's change to pink, the official color of exponentiation. All right, on the left-hand side, the e and the natural log as inverses will cancel each other out and just leave me with the absolute value of y is equal to, and then I'm going to use this pro technique that I showed you previously. Whoops. This c over here also gets the e to the c. And then whenever I am multiplying with like bases, I'm going to add those things. So it'll look like this. X squared, square root of x squared plus 4 times e to the c. And usually, I bring this e to the c up front. And of course, you can just skip that step and go straight to the front of it, straight to the front of the line. All right, and then we want to remove our absolute value symbols. And when we do, we're going to get a plus or a minus. E to the c, square root of x squared plus 4. Now, it would be really nice if we can take that plus or the minus e to the c and replace it with some sort of constant. It would be really nice if we could rewrite this like this. Y is equal to big ol' C, square root of x squared plus 4. But here's the deal. The deal is this. E to the c, that cannot be 0. As we discussed on that previous one, if there's no possible way to raise e to some sort of power to get 0. But look at this. The c value that I have right here, it totally can be 0, right? Because it just is some sort of constant. So in order to be able to replace that without some sort of note that says that c cannot be equal to 0, you just test it. So that's what we're going to do. We're going to test to see if y equals 0 is a solution. And to do that, I need my differential equation, which is right up here. I got my x squared plus 4 dy dx is equal to x times y. So we do need a derivative, which should be a piece of cake, is 0. So both the equation, y equals 0, and the derivative, both of them are equal to 0. So let's just test that right over here. I'd have x squared plus 4 times dy dx, in this case 0, is equal to x times my y equation, which is also 0. I got something times 0 is equal to something else times 0, checks out. So I just checked to verify that y equals 0 is indeed a solution. This means that when we rewrote our differential equation, oh, that's getting messy here. I'll just rewrite it one more time. When we rewrote our differential equation with this c in it, there's no limitation on that value of c. It can be positive, it can be negative, or even 0. Okay, and that's going to end this particular video where we looked at some pro tips, some pro techniques on dealing with absolute values and this e to the c stuff, and solved a couple of differential equations. So again, in the next video, do I have a graph for that? No, I don't. We're just going to look at some more differential equations, get some more practice with separating the variables.